comes with department sharing. So today, the plan is that we're going to finish chapter 3, and then we are going to start into chapter 4. Your chapter 3 homework, as I mentioned at the end of that class last Wednesday, we didn't quite get far enough for you to finish chapter 3 homework. So it's going to be due Wednesday. And I would like you to submit that in hard copy in class, so please bring a photocopy of the thing, as I mentioned before. But what we'll do today is we'll get a chance to really thoroughly go through the equations and such that you're going to be needing to do for that homework. And then we'll even probably start applying that in chapter 4 when we talk about what happens when memory potentials get disrupted. Okay? So before I start, any questions about the course thus far? All right. All right. So I think where we ended, work you thing, we kind of ended around here. And the idea here is that, or what we were talking about is what happens when you're starting to look at memory potentials that have multiple ions that are permeable. So in situations like we started with in this dialogue, in situations where there's only one ion that's permeable, the ion is going to flow across the membrane until it causes the memory potential to change until it reaches that equilibrium potential, at which point there'll be no more flux of that ion. And if that's the only ion that's moving across the membrane, there won't be any more change in the memory potential either. So if you start off with a membrane, a theoretical membrane, and you only were to open a potassium channel, in most neurons, based on the concentration differences that I gave you in the last class between the inside and outside of the membrane, in most neurons you're going to end up with the equilibrium potential of potassium being about minus 80 millivolts. So if potassium is the only ion that's going across the membrane, then the memory potential should end up right around minus 80 millivolts. If, on the other hand, it was just a sodium channel that was opened, that would cause the memory potential to shift until you got to plus 62 millivolts. And that's absolutely what those Nernst equations were telling us. That's the equilibrium potential for those ions. And so that's the memory potential at which there'd be no more net flux of that ion. And conversely, that's basically what the memory potential, you could think of it as that the equilibrium potential is kind of like the memory potential that the ion is going to push the membrane towards. So if sodium is the only ion that can get through, it'll push the membrane potential over to plus 62 millivolts. But if both of these channels were open, then you'd probably get to a situation where you're somewhere in between, right? So you've got potassium moving across the membrane such that it's driving the memory potential towards minus 80, but sodium is moving across the membrane to drive the memory potential towards plus 62. So if both of them are equally permeable, so if there's equal numbers of channels for the two ions, then you'd expect the memory potential to end up somewhere in between. You'd never get to the equilibrium potential of potassium, and you never get to it for sodium. You'd be somewhere in the close to zero, maybe a little bit on the negative side, just because potassium has a little bit larger concentration gradient than sodium. If, on the other hand, if you just sort of follow along with that logic, if you get to a situation where the memory potential is mostly just permeable to potassium, that would drive the membrane such that it would get really close to potassium's potassium's equilibrium potential. But because if sodium at least had some minor amount of permeability, so this last bit is saying maybe sodium or potassium is 40 times as permeable as sodium. So there, potassium's driving most of the effect. Most of the ions that could get across the membrane have to be potassium. But there might be a little bit of a sodium, and so sodium would drive you, instead of being at minus 80, maybe you're pushing up towards, maybe you're at minus 72 or minus 70 by having a little bit of permeability to the sodium. Okay? And that's actually what most of our membranes look like. They have lots and lots of what are called potassium leak channels that allow potassium to stream out of cells all the time. And they have a small number of sodium leak channels. They're there, and they're meaningful. They do cause a difference, but they're vastly outnumbered by potassium. So for the most part, the memory potential is pushed very much closer to potassium's equilibrium potential than sodium's. I do have a video that I like to show for this. This is a video I ripped out of an A&P textbook. Well, really, I ripped it off their website. Let's see here. Oop, I'm in the wrong directory. Oh, you can't see that. Hang on a moment. I gotta get sound connected for this to work. Let's hope. So, assuming the sound works, it does a pretty good job of explaining and demonstrating this sort of competing effect of potassium and sodium on the resting membrane potential. So let's see if this works. Probably helps to make sure. Oh, come on.
The human brain alone contains about 100 billion nerve cells called neurons. A neuron, like every other cell, has positively and negatively charged ions inside and outside. Further, a resting neuron has a greater negative charge on the inside surface of the plasma membrane and a greater positive charge on the outside surface. This partitioning of charge creates a voltage difference across the membrane known as the resting membrane potential, which can be measured using a voltmeter. On average, an intracellular electrode records a value of -70 millivolts. The resting membrane potential depends on two factors. First, it depends on the presence of sodium and potassium gradients across the plasma membrane. Specifically, there are more sodium ions outside the neuron than inside, and more potassium ions inside the neuron than outside. Second, the resting membrane potential depends on the differential permeability of the plasma membrane to sodium and potassium ions. Leak channels in the plasma membrane allow sodium and potassium ions to diffuse or leak down their concentration gradients. The membrane contains many more potassium leak channels than sodium leak channels. Thus, the membrane is much more permeable, or leaky, to potassium ions. As positively charged potassium ions leak out of the neuron, the inside surface of the membrane becomes negatively charged compared to the outside surface. If potassium was the only ion moving, the potential would stabilize at -90 millivolts. However, positively charged sodium ions leak into the neuron, which slightly offsets the negative charge and raises the voltmeter reading to -70 millivolts. Sodium-potassium pumps actively transport sodium ions out of the neuron and potassium ions back in, compensating for the sodium and potassium leaks. Thus, the pumps help to maintain the resting membrane potential.
Okay, so questions thus far. Is that all making sense? Oops. So what I like about that, hang on. I thought I paused you. What I like about that thing, I think that video does a really nice job of kind of summing up most of what we've done thus far, with the exception of actually calculating Nernst equation. It doesn't do that for us. But aside from that, it gives us a pretty complete picture of, first, the establishment of the concentration gradients by these sodium-potassium pumps. And then the fact that we've got sodium and potassium flowing across the membrane, and is doing so in this way where potassium is far more permeable than sodium. And therefore, potassium is going to drive most of the change in voltage, because there's many more positively charged potassium ions flowing out of the membrane than there are sodium ions coming in, just because there's so many more channels for potassium. So potassium gets the biggest say in what the membrane potential will be, is a way to think about it. Okay? So what we want to be able to do then is try to actually quantify this difference, right? So to go beyond just strictly saying, well, because there's more potassium, it's going to be more negative, the membrane potential will be more negative, it'll be closer to potassium's equilibrium potential. We can actually calculate the specific membrane potential that a membrane will be for a given set of sodium and potassium concentration differences and sodium and potassium permeabilities. And that's what this next equation is going to do for us. It's called the Goldman equation. I've also seen it called the Goldman-Hodgkin-Katz equation for the original paper in which the thing was published. This should look vaguely similar to the Nernst equation. So if you look at the Nernst equation is this. Let me draw it up here. Whoops. It's 61.54 millivolts divided by the charge times the logarithm of the concentration outside divided by the concentration inside. That's the Nernst equation. This one has a lot of those same things, right? So it's got 61.54 millivolts. It's the same constant, and that is dependent at 37 degrees Celsius, which is what we'll always be in this class. That number would vary if you're at a different temperature. But we've got also, you'll notice for each of the different ions that are mentioned in the equation, you've got a concentration outside and a concentration inside, and usually it's the same one, so it's concentration outside divided by concentration inside for potassium, and the same is true for sodium. Maybe not for chloride, but that's just the way it is. And there are some differences, right? I mean, for one thing, we've got multiple ions now that we're considering. The Nernst equation is strictly about calculating the equilibrium potential, which would be the membrane potential that your ion would shift the membrane potential to if it was the only ion that was permeable in a membrane. Now we've got potassium in here, we've got sodium in here, we've got chloride in here. You could modify the equation in such a way to allow us to add other ions if we wished, like calcium would be maybe the major one that we'd want to think about. But we're just going to stick with this version of it, okay? So just to run down the terms, the other thing, in addition to having more than one ion present, is we also have these direct measures of permeability, and it's a relative permeability, so it's a unitless value. It's all one. The way this works is it's always going to be the permeability of one ion versus the other. So if we had a membrane where the permeability to potassium, pK, is 40 times that of the permeability of sodium, which is pNa, you could plug in the number 40 for pK here, and you could plug in the number 1 for pNa in this situation, right? And if chloride wasn't permeable at all, you could plug in a 0 for the permeability of chloride, if you wanted. And it can be any other variant you want. So if they had equal permeabilities, you could set all the numbers to be the same value, so they could all be, P equal to 1 if you want, if they all had the same permeability. If sodium was twice as permeable as potassium, you could have 2 here for pNa and 1 here for pK. You can put whatever numbers you want based on the situation that you're dealing with here. It's really flexible, and you don't have to worry about units again with these permeability values. They're all relative to each other. It's kind of just weighting one part of the equation versus the other. But what this equation is going to let us do is, for a given set of concentrations inside and outside membranes, and for a given set of permeabilities, this does a really, really good job of calculating what the membrane potential is actually going to be in those circumstances. And then the great thing about this, as we'll see in the next chapter, is we can start playing with these numbers. So if we say, hey, what would happen if we opened a bunch of sodium channels? Well, we could increase the permeability to sodium and see how that shifts the membrane potential, right? So we could just, bump the number from 1 to 20 if we wanted, or 200. Yeah?
Is permeability for potassium the same for outside and inside?
Yeah, so permeability is referring to the rate or the ease with which the ion gets across the membrane. So it's not dependent on inside-outside. It's a property of the membrane itself. Yeah, good question. Other questions about this so far? A couple things I'll point out. Well, here, let's try this. Before I point out how to actually use the equation, let's actually try to do a calculation here. So here's this equation. There's the Goldman equation up top, and here are a set of ion concentrations. These are the same concentrations that I gave you before. So you'll need your calculator for this thing. And I'm going to give you this situation that I was just describing, where the permeability of potassium is 40 times that of sodium. So I put a 40 here for pK and a 1 here for pNa. I mean, it would work. I could put an 80 and a 2 here, and it would give us the same number. It's just the relative permeability. So potassium's permeability is 40 times that of sodium's. And we'll assume for now that chloride is not permeable and therefore doesn't matter. You'll see what happens, right? If I put the permeability of chloride to be 0, all of a sudden this whole thing, 0 times any concentration of chloride is 0. So the whole bit about chloride over here doesn't matter anymore. Okay? One thing I'll point out as you're plugging numbers in is that this whole numerator up here is all, effectively, that's like all in parentheses. So you have to do this entire stretch here before you divide by what's down here in the denominator, right? It's not pk times k out divided by pk times k in. It's pk times k out plus pna times na out. And you have to do all of that before you do any division. So you have to be really worried about your order of operations in this when you're doing these equations. So I'd like you to go for it on this equation, or this for these permeabilities, and then try it again if we increase sodium's permeability so that instead of 1, it's 200. But I didn't bring my numbers. So I wrote out the equation. I plugged in all the blanks, right? So I'm just plugging all the numbers in, just to be straightforward. And then again, the way my iPhone calculator works, because it's less nice than some of the fancy pants ones, is that I need to do everything that's up here on the numerator first, and then everything that's down here in the denominator, and then divide the two. I'm sorry. So that's 350, I got 350 millimolar, so that's basically 40 times 5 plus 150. This term is 0, right? Because 0 times 13 is 0. This one I got 40 times 100, that's 4,000, plus 15, so I got 15 millimolar. I divide these two, millimolars cancel. I get a small number. I hit the log button, and I got like minus 1 point something. And I multiplied that by 61.54, and I got minus 65 millivolts, or thereabouts. Like, right? Let me get something very, very different. Pretty sure this is right. That's about where I want it to be. What, did anybody get the other one? What'd you get?
39.
Plus 39. So if we use plus 200 for the permeability for sodium, you got plus 39, you said?
Yeah.
Did anybody else get plus 39? I just didn't run through it or remember to bring the numbers, but that sounds about where it should be. So you see what happened, right? The concentrations, if we, instead of doing it this way, if all we do in this equation is we change the permeability for sodium from 1 to 200, that causes us to shift from minus 65 millivolts all the way up to plus 39 millivolts. That's what I've done here. So we've shifted the charge. This is a massive swing in memory potential, despite the fact that the concentrations didn't change at all, right? The only thing that's different is now sodium is 5 times as permeable as potassium, whereas before it was a 40th as permeable as potassium. So we did a massive increase in sodium permeability. And what that does is that it emphasizes this part of the equation. This sodium part of the equation becomes much more influential as the permeability of sodium increases. So effectively, in real life, what's happened is we've increased the number of sodium channels that would be open, which allows much more sodium to flow across. And because there's, in a typical cell, there's high concentration of sodium outside, which is 150 millimolar, versus a low concentration of sodium inside, sodium's going to flow inward and bring its positive charges in, which will make the inside of the membrane more positive. And we're shifting from minus 65 all the way up to plus 39, so that's showing that positive increase in memory potential. Okay? So you should be able to plug in numbers for these equations. And even more so, I think it's really important that you understand what they're doing for us. So this equation is allowing us to balance, basically, the influence of sodium versus potassium on the membrane potential. And the more permeable an ion is, the more influence it has, and the closer it will drive the membrane potential towards its equilibrium potential. So you might remember, just to sort of reference you again, the equilibrium potential of potassium was about minus 80 millivolts. So when potassium's much more permeable than sodium, the membrane potential ends up down here at minus 65 millivolts, which is pretty close to its equilibrium potential. But when we then shift the equation around to make sodium more permeable, now the equilibrium potential of sodium would be still plus 62 or so, I think, is what number we had before. So if sodium's permeability or equilibrium potential is plus 62, and we increase permeability to sodium, now sodium is going to drive the membrane potential as it flows inward closer to its equilibrium potential of plus 62, and in this case the Goldman equation tells us it'll drive it all the way to plus 39 millivolts. Okay? So it's pretty slick. I mean, I really like this thing. And we could do even more, and in fact on the homework I'll give you a chance to do more. This one's kind of interesting. We could just sort of do a what if here. So this last one says, what if the permeability to potassium was 40 and the permeability of sodium was 0 now? So we're the same as here, but we're setting permeability of sodium to 0. Permeability of chloride we'll keep at 0 for now. So what should happen then? Without plugging the numbers in, let's just look at it, right? So if we set this to 0, so the permeability of sodium is 0 now, permeability of chloride is 0 now, that basically means the sodium part doesn't matter. We could kind of cross it out because anything times 0 is 0. So all we're left with is the potassium part of the equation. So now we've got 61.54 millivolts times the logarithm. Well, actually, the permeabilities now are canceling out. We could do that now. So it's just 61.54 times the log of potassium outside divided by potassium inside, which is that, right? That's, the thing becomes the Nernst equation when you only have one ion that's permeable. You see that? I mean, we're assuming plus 1. The charge here has to be plus 1 for that to work, as we've sort of set it up here. But that becomes, again, it becomes the Nernst equation once you reduce down to and only have one ion that's permeable. So that's saying that the membrane potential, the Vm, so that's the voltage of the membrane potential will equal the equilibrium potential when only one ion is permeable. It's just kind of proving what we've already said. Last point I'll make. Why do you think chloride, the concentration of chloride is inside divided by outside instead of out divided by in the Goldman equation? Like, why would that be? It's a negatively charged ion. Yeah, so that's the key thing. So because we're doing a logarithm here, effectively the only thing you have to do is if you invert these numbers, that basically is the same as getting a negative charge once you take the log of the thing. So this allows us to get away from having that Z term because Z is going to be different for each of these different ions. So because chloride is negative, you have to invert concentration in divided by out instead of it being out divided by in for the other two ions. Any questions? Yeah.
So is it always going to be switched if it's a negative ion?
Yes. And I'm never, yeah. If it's a negatively charged ion, and the only one of those I'll ever do is chloride on you. But it would be reversed in that case. And I think on the homework, it does ask you to deal with chloride. I'm sort of skipping that for now, but you'll do it on the homework. You just treat it the same way. You just, it's another thing to put into the numerator and then the denominator as you're doing the calculations. Calcium, you'd have to do more of a futz with it because it's a double positive charge, and we're never going to go there. We're just not bothering with it. Yeah.
And you can use this equation with other ions.
You could, yeah. So like it doesn't really matter what ions you put in here. If I had, what's a +1 charge? Lithium. just for ducts. I could sub in lithium here, and it would work the same way because it's a +1 charge. What else has a +1 charge? I don't know. I'm getting pretty far down the periodic table to get other +1 charge things. But yeah, if it's a +1 charge, you could swap it out for one of these. If it was a fluoride ion or something, you could swap it out for chloride. If you start getting into +2, +3 charges, then it gets screwy. We're not going to go there. For the most part, we're going to be handling sodium and potassium and chloride. Yeah? So I will give you all the equations, but you have to know how to use them. I'm not going to label them. So it would look like that for the Nernst equation, or it would look like that for the Goldman equation. So you need to know how to use the thing, but I'll give you the thing.
Will we ever have to rearrange it to solve?
No. Not this one. Yeah. Other questions? Okay. So it's worth, these aren't really hard. They're just, honestly, they're more tedious than hard, right? Like once you get it, you're just multiplying numbers and then, adding them and then multiplying them and, dividing and all this jazz. It's not difficult calculations, but it is tedious, and it is something you have to be careful because it's very easy to screw something up, and then that negatively affects, the answer that you get. Okay, I have one other equation I want to show you that has to do with all these things, and we've been kind of making reference to some of the terms, and this is called Ohm's law. So Ohm's law is given as, there's two variants on it. So I actually learned it in high school, and this is just how I always remember it. Where's my markers? I learned it as V equals IR, and I don't know why. For some reason that's easier for me to remember. But that just rearranges to I equals V divided by R. If I divide both sides by R, I'm there. So basically what this is allowing us to do is try to understand the relationships between these voltages we just were calculating and some of these other terms we've been kind of referencing. And those would be current, which is just, in the case of a neuron, we're talking about the rate of ion movement. So really what we're talking about is the flow of ions from one side of the memory to the other when we're talking about a current. And we could measure that in milliamps typically. In fact, I think that's listed here. You could measure it in amps too if you were that high. But for the most part, in biological systems, we'll be measuring it in milliamps. You've got these other terms. So in this case, it's you can set I current is equal to G, which is called the conductance. Conductance is basically the ease of flow of an ion across a membrane. I will more or less make this synonymous with permeability. Permeability is really specific to ions, but for our purposes, we're dealing with ions moving across and being permeable across a membrane. So conductance of an ion is effectively how easily it can get across. The other way to express conductance is by its inverse, though, which is just resistance. So if conductance is how easy it is for an ion to get across, if you divide that number, 1 divided by that number, you get the resistance, which is just how hard it is to get across the membrane. And they're really kind of the same thing. So you can express Ohm's law in terms of a resistance, as it is on the right over here, or you can express it in terms of conductance, and it's telling you the same thing. And then finally, the V, that's what's referred to as an electrical potential. That's basically just a charge difference across the membrane. And you can think of it as this is the force that would be applied to ions that would cause them to move across a membrane or through a circuit. So in this example down here, they're kind of going to a situation where they're sort of equating sort of a non-biological example, where you've got current that could flow across this battery. And in this situation, the current is established, the voltage is established by this battery. And we're looking at how ions could move across this membrane that's described here. Now in this case, they're saying the voltage difference here that's driven and caused by this battery is 1.5 volts. That's what typically, like a AA battery, if you look at the AA battery that you might have, or a AAA battery, they're 1.5 volts. So that's where that number's coming from. And in this case, they're saying the conductance of these ions in this case would be 0 Siemens. This is the unit for conductance. And it's 0 because in this case, you'll note there's no channels that are drawn across that membrane. So there's really no way for them to get across. As a result, they have 0 conductance. So the question is, under those circumstances, what would be the current in amps? I think you can just do this one in your head, right? What would our current be, given these numbers? 0, right? So G is 0, V is 1.5, so 0 times 1.5 would be 0. So that's saying that we have no movement of ions across this membrane in a situation where there's no permeability, there's no conductance of those ions, right? We've got no channels, they can't get across. In contrast, if we open up some channels and allow ions to flow across the membrane, which is what's happened over here on the right, so we've still got a voltage of 1.5 volts, we've got a conductance of 5 Siemens, now we can calculate the current, it'll be 1.5 times 5, which is 7.5, right? So that'd be 7.5 amps in this case. Now look, I'm not going to be stressing too much about using this equation. I think it's much, for our purposes, it's much more important to be worried about using the Nernst equation and the Goldman equation, being focused on those. But you should understand the relationships between the voltage and the conductance and the current, and frankly how the resistance fits into that too, which is described by this in kind of qualitative terms, such that if we're talking about a biological membrane and we're interested in what should happen as we open channels, you should be able to apply this, this equation, at least in conceptual basis, and say, okay, if we open channels, we're going to increase the conductance of that ion across the membrane. And so as long as there's a voltage, a charge difference, then we should get flow of ions. We should have a current moving across the membrane. Okay? So we'll see terms like electrical potential, because we're calculating membrane potentials using the Goldman equation. We'll mention sometimes conductance, sort of interchangeably with permeability. We'll talk about resistance when we talk about membrane resistance as far as how hard it is for ions to get across. And we'll talk about current sometimes, which is just ions flowing around. So I want you to have basic familiarity with that equation too. But we're not going to be doing like a lot, much in the way of problems with it. Okay, so here's sort of key points summarizing all this stuff. Memory potentials are driven by movements of ions across membranes, and the ions movement is going to be determined by the concentration gradients as well as electrical gradients that might be present. So what that's saying is that if you start with no electrical gradient and you have a concentration gradient, and you allow one ion to start flowing across the membrane, that'll create an electrical gradient. That's what these little, cells where you draw a little arrow and you point and you figure out what the memory potential will be. And you'll have eventually a situation, if there's only one ion permeable, where you'll reach the equilibrium potential where the electrical gradient is sufficient to balance the concentration gradient. And you'll get no net flux of that ion. In a real cell, membrane potential is always going to be dominated by the most permeable ions. So if only one ion is permeable, the cell's membrane potential will change until it reaches that ion's equilibrium potential. And we can calculate the equilibrium potential using the Nernst equation, which is what I drew over here. If several ions are permeable, which is almost always true in real life, then the membrane potential will be intermediate between the equilibrium potentials of the ions, and we can calculate that membrane potential using the Goldman equation, which is this guy. And this allows us to properly weight the concentration gradients as well as the relative permeabilities to calculate what this membrane potential will be in this real cell. And as a final note, in actual resting neuronal membranes, potassium is almost always the most permeable ion. There's a few exceptions to that, like the hair cells of your inner ear, of your cochlea, are weird, and this is not true there, but it's almost always true, where potassium is the most permeable ion, and sodium is much less permeable in a resting state. And therefore, most resting membrane potentials lie really close to the equilibrium potential of potassium. Cool? All right. I have one other last little topic, and that'll kind of finish off the chapter. So I spent a lot more time on that than I had planned to, but at the same time, I think that's good. That's good practice. And so that'll set you up to be in good shape to do the homework. And the homework, again, I'll be doing Wednesday. I do want to talk about these potassium channels, because we've been talking about the fact that we have lots and lots of potassium leak channels that are plugged into any given membrane. And those potassium leak channels, they have a particular structure that allows them to function in the way that they do. So if we're looking for potassium channels, I think that the really interesting thing about a potassium channel is that these things are really specific. So, there's not that much difference between a potassium ion and a sodium ion, really. I mean, sodium ions are a little smaller, but they're both positively charged ions, a +1 charge. Potassium is right under sodium on the periodic table. So I think it's pretty interesting to try to ask and understand how, what are potassium channels structured as, and why is it that they're so darn specific? So there was a major effort, once we started to realize how important potassium was, there was a major effort to go and find these potassium channels. And the first one they found actually was found in Drosophila, which are these little fruit flies, which many things, especially in the 1900s, Drosophila was incredibly important and it still is, as an important model species. And the way they found these potassium channels is they discovered basically a neurological mutant. They called it Shaker. And here's a video that shows why they called it Shaker. Where are you? Basically, when you knock out fruit flies, usually you expose them to carbon dioxide is the typical way you do it, and they just sort of fall asleep. And they're much more resilient in that, usually in a vertebrate, if you expose a vertebrate to carbon dioxide, that is what a gas chamber is, and they don't tend to survive that process. But these guys do. But as they wake up, usually what you'll see is that most Drosophila will start to twitch a little bit as they're waking up after they've been dosed with their anesthetic. And what they found is that there was one mutant that shook quite a bit more than the typical Drosophila does as it's starting to wake up. So this is what you're looking at here. You can see these are the normal ones, and they're twitching, right? But these guys are going berserk. So this indicated that whatever mutation they had found in this particular video, this is a mutation that it did something to their nervous system. They didn't really know what, but this is what they're looking for, is any kind of nervous system variant mutation that they could then investigate and see if that particular mutant might help them hone in on a particular channel. And in fact, it did help them find the first potassium channel that was ever really characterized well. So the way these channels are set up is they're composed of a series of subunits. They have a common basic structure. So basically, each potassium channel is composed of 4 subunits, and the subunits are just kind of repeated, and they glom together where each one forms sort of 1/4 of the wall of a channel. It's basically functioning as a tube. And the reason that these things are so specific to potassium has to do with one specific amino acid domain. So if you look at the zoomed in structure of one of these subunits, it kind of looks like this, where you've got one long protein chain, which is what's shown here. And each chain is sort of divided into different domains, and these are all alpha helices that are sort of all lumped together to form this sort of semicircular structure. And the way these proteins get folded, there's one little loop, it's called the pore loop of amino acids, that's sort of separate from these alpha helix chains, that ends up being plugged on the inside of the membrane. And so each of these 4 subunits would have their own pore loop. Okay? And it turns out that this pore loop is really the key thing that allows them to be specific to potassium ions. And this has been verified in other kinds of animals too. So the first time we found a potassium structure or potassium channel was in Drosophila. There's been subsequent work on mice, for example, and all kinds of other animals at this point. This is sort of summarizing a long series of studies where there's a mouse strain called Weaver that had a mutation in this particular pore loop that caused that channel to be less specific to potassium and to let sodium ions come through at a decent rate. But this is how the specificity works. So again, sort of imagine that each of those 4 subunits has a pore loop. So all the pore loops are kind of coming in and creating the lining of the channel through which the potassium ion has to fit through. It turns out that they are structured in a very specific size, to a very specific size relationship. So sort of imagine this is one pore loop from one subunit. This would be the pore loop from another subunit. And these things that are in here are either the potassium ions or water molecules that they're interacting with. And it turns out that the specific amino acid domains that are kind of pointed inward into the interior of the channel are of the appropriate polarity and of the appropriate distance, that they do a really good job of mimicking the oxygens of water molecules, where most of the time potassium is surrounded by water molecules as it's suspended in solution, as it's dissolved in solution. So basically, these amino acids kind of substitute for those water molecules right along the interior, and they're exactly spaced such that they are perfectly the right size and dimensions for potassium to fit through. Whereas sodium ions, while they're a little bit smaller, you'd think they'd be able to go right through, they tend to bring water molecules with them, and that sort of water-sodium complex can't fit through the exact spacing that's set in here. So that really only potassium ions are able to get through along with some water molecules at the same time. Okay, so again, without getting into too much of the nitty-gritty details, the key thing is that these pore loops, let me go back, these pore loops that exist on each of the 4 subunits have very particular polar properties and spacing such that they allow potassium ions alone to get through, and sodium ions really have very little permeability. Okay? Bless you. Any questions? All right. So what's left then are these homeworks. I thought we'd get further along than we did today, but I'm just going to end it there. So we'll start at the beginning of class on Wednesday. We'll go through those equations. It really shouldn't take us very long. So bring 2 copies, 1 photocopy and 1 original copy. Turn in the original. You keep the photocopy. And we'll talk about these homework questions and then launch straight into chapter 4. So I will see you guys then.